So that example gave us the properties of the graph and for us to sketch it out. For the next examples, we're just given a function where it wants us to perform a full curve sketching analysis and sketch out the graph. So remember, we're just following those steps that it said in the beginning. Step 1 is domain. In this case, looking at the denominator, x cannot equal 0. Step 2 was the intercepts. I have my x-intercept. I have my y-intercept. For the x-intercept, if 0 is equal to x squared minus 1, all divided by x cubed. When I multiply both sides by x cubed, it's still just going to be 0. So 0 is equal to x squared minus 1, which means that 1 is equal to x squared, which means that x is equal to positive or negative 1. Or I'm going to have x-intercepts at 1 and 0 and negative 1 and 0. For the y-intercept, if I try and take f of 0, I get 0 squared minus 1, all divided by 0 cubed. I can't divide by 0. So the y-intercept does not exist. This is going to occur right on the y-axis for the vertical asymptote. Step 3 was symmetry. We're going to check the relationship between x and negative x. So if f of negative x is equal to negative x squared minus 1, all divided by negative x cubed, that's going to give me positive x squared minus 1 all over negative x cubed. So because f of negative x is the same as the negative f of x, this is going to be odd and be rotationally symmetrical. Step 4, the asymptotes. So we need to look for vertical asymptotes. We need to look for horizontal asymptotes. The vertical asymptote, in this case, from the domain, was when x was equal to 0. So what's happening when x is equal to 0? Limit as x approaches 0 from the left for x squared minus 1, all divided by x cubed, is going to give me a very small negative number squared minus 1 divided by a very small negative number cubed, which is going to give me positive infinity. So as it's approaching from the left, it's going to shoot up to positive infinity. We take the limit as x approaches 0 from the right for x squared minus 1, all divided by x cubed. That's going to give me a positive, very small number, squared minus 1, all divided by a positive, very small number, cubed, which is going to give me a value approaching negative infinity. For the horizontal asymptote, remember, we're looking at what is happening as the limit approaches positive or negative infinity. So I'm going to multiply every single term on the top and the bottom by 1 over x cubed. And that's going to give me the limit as x approaches positive or negative infinity for x squared over x cubed minus 1 over x cubed divided by x cubed over x cubed this is going to become 0, this is going to become 0, and this is just going to become 1. Which means that this limit is going to approach 0 over 1, which means it's just going to approach 0. So I have a horizontal asymptote at y is equal to 0. Part 5, we're looking at intervals of increase and decrease. So remember, for this, we need to find f prime of x from our original function. F of x was equal to x squared minus 1 all over x cubed. So f prime of x is going to equal x cubed times 2x minus x squared minus 1 times 3x squared, all divided by x cubed squared, or 2x to the 4 minus 3x squared times x squared minus 1, all divided by x to the 6. I'm going to factor. I'm going to pull out a x squared. And I get 2x squared minus 3 times x squared minus 1 all over x to the 6. Where I can take out 2x's from here and 2x's from here. And that's going to give me negative x squared plus 3 all divided by x to the 4 I'm going to factor out a negative from the top. Oh, minus 3. And I'm going to take a difference of squares. My critical number from the numerator is going to be x is equal to positive or negative root 3. My significant number from the denominator is going to be x equals 0. Because remember, it's still significant, but it didn't exist in my original function because that was part of my domain. Critical numbers have to exist in that original function.